Welcome back. It's time to learn another data structure. This is a big one, and an exciting one at that, because it's going to introduce a lot of new topics, especially when we get into algorithms as well. They're called trees. And no, not these kind of trees, more like this. Trees are a data structure that have what we call a hierarchical structure. As opposed to something like linked lists or arrays, which are linear, trees can have 0 or more child nodes. You see, a tree usually starts with a single root node or a parent node, and every child of the tree descends from this root node. So it's kind of like an inverse tree, really. And every child of a node descends from only one parent. So you have a parent-child relationship that you see is unidirectional, that is, it's going one way. And you also have leaf nodes, which are the very end of a tree data structure. Finally, within a tree, you can have things like subtrees, such as the area over here circled in red. 3, 6, 7 form a subtree. And tree data structures are very important because you work with them every day. If we go to twitter.com or any website for that matter, and we open the developer tools, just like I did here, if I go to the Elements tab, you see our web pages are created by something called the DOM, or the Document Object Model. And this is a tree data structure. It doesn't look like a tree that I just showed you, but the browser is just making it look nice. But underneath it, we have head and body that are children of the HTML tag. Inside the body, we have all these children. And inside these children, we have more children, and they're all connected hierarchically to one another. I'm sure everybody has tried to play chess online versus a computer. Well, a computer in a chess game, at least back in the day before we had things like machine learning, used a tree data structure to make a decision. Should I make this move? Or should I make that move? Or should I make that move? And it would pick moves based on which move had the better outcome. Facebook comments, for example, are a tree data structure where I can comment on a friend's photo and that friend can comment on my comment. Family trees can be represented in a tree data structure. And for us engineers and programmers, you might have heard of the abstract syntax tree. If I Google abstract syntax tree here, well, this is how programs or code is usually being run. Usually we write code and then it gets broken down by the machine into this abstract syntax tree so that it understands what we wrote down. And this, as you can see, uses a tree data structure. The beauty of trees is that we use the same principle as we did in linked lists. That is, we have nodes. And these nodes can contain any type of information that we want. We can have user information, we can just have numbers like we have here. Anything we want, we can contain within a node. Now you might be thinking, this kind of reminds me of a linked list. And you'd be right. Linked list is technically a type of tree, but with just one single path. And it's linear. There's only one way to go from top to bottom versus what we've seen before in a normal tree, like this one. Now, a thing to keep in mind here that might be different than a linked list is that a node can only point to a child. As you can see, all the arrows point down. There's always one entry point, which is the root, but nodes don't really have to reference their parent. Now, just like in real life, there are many types of tree data structures that we can have. And if you go to Wikipedia and you look for all the tree data structures, it's going to, well, intimidate you, that's for sure. Because look how many different types of trees we have. Just like in real life, how we have all these different types of trees, there's different types of trees that we can have for a specific use case. But don't get overwhelmed. In this course, we're going to go over the main ones that get used, I would say, 90% of the time. And the ones that you're most likely going to encounter during an interview. Because at the end of the day, once you understand what a tree data structure is like, how to create it, how to perhaps use some actions on it, then all the other trees that you saw are just minor alterations to what we know. Now, I want to warn you. Back in the day when I took a class on data structures, this part, especially trees, really dragged on. and made me not interested in data structures because there's so many things you can talk about when it comes to trees. I'm going to try and keep you engaged to the best of my ability and try and be efficient through this section and show you the important aspects that you need to know for an interview and to lay the foundation, not to teach you every single tree that there is, which is not going to benefit you. With that in mind, I'll see you in the next video. Bye-bye. Welcome back. We're now into the tree data structure section, right over here. And as we can see, trees or linked lists are a type of a tree that we've already talked about. But there's a few others over here that we have yet to talk about. So we're going to cover that and get familiar with the main different types by starting off with binary tree. Let's get into it. A binary tree is something you've likely seen before. And it's a type of tree with a few rules that are applied to it. But they're quite straightforward. Each node can only have either 0, 1, or 2 nodes. And each child can only have one parent. This is a binary tree. However, this is not a binary tree because it has 3 children, or at least one of the nodes has 3 children. And each node represents a certain state. And this is very similar to what we've done in the past, especially with linked lists. If we take a look at an example here, in order for me to create a binary tree, well, I can just create a function, say binary tree. And this binary tree perhaps will get a value. And the binary tree, or in our case, let's just do a binary tree node, will simply have a this.value associated with it, which is the value that we give it inside of the function. And then we have 2 other properties, which is a pointer to the left side of the tree, which for now will be null, and a pointer to the right side of the tree, that is this.right equals null. And that's it. We can represent a binary tree node as simply having a value and then a left and a right property. Very similar to what we did, or a very similar principle to what we did with linked lists. Now, we're going to actually code a tree and create a tree data structure just like we have for past data structures. But I want to also point out a few terminology that we might come across and that are important. In this case, we're looking at something called a tree that is completely full. That means there are no gaps in the tree. Let me show you what I mean. A perfect binary tree has everything filled in. That means all the leaf nodes are full, and there's no node that only has 1 child. A node either has 0 children or 2 children. And also, the bottom layer of the tree is completely filled. Nothing's missing. Versus a full binary tree, which simply says that a node has either 0 or 2 children, but never 1 child. Now, why is this important? Because this type of binary tree, especially a perfect binary tree, is really, really efficient and something that is desirable. When binary trees are perfect like this, they have 2 really interesting properties. One is that the number of total nodes on each level doubles as we move down the tree. For example, here we have 1 node. In the next level, we have 2. So we've just doubled the nodes. In the next level, we have 1, 2, 3, 4. So we've doubled 2 to 4. If we had another level that's a perfect binary tree, we'd have 1, 2, 3, 4, 5, 6, 7, 8. So we were doubling every time. The second important property is that the number of nodes on the last level is equal to the sum of the number of nodes on all the other levels plus 1. All right, that was confusing. What do I mean? Well, here, if I take the bottom level, that is 1, 2, 3, 4, the second property states that all the nodes above it plus 1 is going to equal the bottom level. So 1, 2, 3 plus 1 equals 4. That is what we had on the bottom. Which means, in other words, that about half of our nodes are on the last level. And this brings up a really interesting point. By organizing our data in this way, we have half of this data in the bottom level. If somehow we can avoid visiting every node, even if the node we're looking for is at the very bottom, perhaps there is some efficiencies that we can have. And you'd be right. Because of this type of structure, you're going to see a new notation of big O. Something that we've been waiting for a long time, O log n. And when we start talking about something called binary search trees, you're going to start seeing this notation. Yes, we finally got into another big O notation. But what does it mean? In the next video, I want to talk about O log n and why trees allow us to have something like this and what the implications are. I'll see you in the next one. Bye-bye. Welcome back. In the previous video, we talked about a special characteristic or properties of binary trees. And because of the way binary trees are structured, there's a certain way for us to calculate the number of nodes that they have. For example, on level 0 of a binary tree, that is the very top level where we only have one root node, we can calculate how many nodes there are by doing 2 to the power of the level, which is 0. So if I do 2 to the power of 0, it's going to equal 1. That is, we have one node. If we go a level down and say, what about level 1? How many levels do we have? Well, we have 2 to the power of 1, which equals 2. All right, let's keep going. What about level 2? How many nodes in total do we have on that level? Well, we have 2 to the power of 2, which is equal to 4. And then one last level, let's say level 3. How many nodes are we going to have in level 3 in a perfectly balanced binary tree? Well, 2 to the power of 3 is going to equal 8. Oh boy. We just did some math here, and I promise that this course isn't going to be that mathy, but bear with me here. I want to explain to you what O log n means. Knowing what we just did now, and knowing that these are the total number of nodes, if we imagine that this data was in an array, that means we have 8 places that we need to iterate through, 8 nodes that we need to check, perhaps to search for something. Well, based on this formula here, that means that we can find out the number of nodes in a tree by doing 2 to the power of h, or the height, that is the level. If we know how many levels our binary tree is, we can find out how many total nodes there are. 2 to the power of h minus 1. Now, why this minus 1? Well, if we go back to our diagram, this binary tree, we have 1, 2, 3, 4, 5, 6, 7. We have 7 total nodes, and the tree is 1, 2, 3. The height of the tree, well, it's 3 levels deep. So 2 to the power of 3 minus 1 is 7 nodes. Now, if we actually simplify this, we can just simply say that the log of nodes is going to equal the height, or the steps. And I use log here, just in case you're wondering. Log simply means that log 100 is equal to 2, because 10 to the power of 2 equals 100. So all I did was, using this, I simplified and said that log nodes is equal to the height, and we've dropped -1 here because it's insignificant. But log nodes is the number of steps, or height, and let's change this to steps that we would use in a tree. Let me show you again in our diagram. Log n simply means that based on the height, the maximum number of decisions, let's say we're looking for a specific node, that we're going to take is going to be log n. That means, is this the node we're looking for? Nope. Then we either go left or right, and let's say we go left and say, is this the node that we're looking for? And that's our second step. If the answer is no, then we either go left or right, and we say, is this the node we're looking for? Yep. So we have maximum 3 steps here, instead of if we went 1, 2, 3, 4, 5, 6, 7 steps. You see that there's some sort of efficiency here. And coming up, we're going to learn about binary search trees, where we're able to minimize those steps instead of visiting every single node. So when you see the notation of O log n, don't get startled. All it's saying is that the choice of the next element on which to perform some sort of action is one of several possibilities, and only one needs to be chosen. We don't have to check both. And a good way to think about log n is when you're looking through a phone book. You don't actually check every single person in a phone book, do you? Instead, you can simply do what's called divide and conquer by looking based on where their names alphabetically begin. You would open up the book to where you think the letter will start with, the name will start with, and then keep dividing and conquering until you get to that person. You only need to explore a subset of each section before you eventually find someone's phone number. So just think of that. O log n is just like looking through a phone book. And the reason that I just talked about O log n in such detail is because it's an important concept. It's really, really fast. As you can see here, O log n is this light green good area. That's even better than O of n, linear time, because we don't need to check every single element. And in the next video, we're going to talk about the most common tree that you're going to see in a lot of places, called binary search tree. And as the name suggests, it allows us to search really efficiently. And just by looking at this graph, you might be able to think about how a place like Google and Google search might find this extremely useful, right? When we search through Google, they have a ton of websites, a ton of nodes to search through. How are they able to give us an answer to our searches so fast? If they used O of n, time complexity, it's going to take a lot of time and it's going to be really expensive for them. So instead, they use a tree structure or a tree data structure so that our searches can be a lot faster with something like O log n. I'll see you in the next video. Bye-bye. Welcome back. Let's continue our discussion with the most common tree data structure. That is the binary search tree, which is a subset of binary tree, which we talked about. What is a binary search tree? Well, a binary search tree are really, really good, as the name suggests, at searching. They're great for comparing things. Now, why would this be better than, let's say, a hash table where we can just give it a key and get the item right away? Well, this data structure preserves relationships. Just like you wouldn't want your folders on your computer to be in a hash table data structure because there is no sort of relationship. Instead, you want your folders to have relationships, to have a parent folder and a subfolder and then a subfolder. A thing like binary search tree allows us to preserve these relationships. When it comes to binary search trees, these are the rules. 1, all child nodes in the tree to the right of the root node must be greater than the current node. That means if I keep going to the right, the number or the value of the node constantly increases. You see over here, I go from 101, 105, 144. If I keep going to the right, let's say here, 33 to 37, that is increasing. If I go to the left, 101, 33, 9, that's always decreasing. Same with here, 105 to 54. If I go to the left, it decreases. To the right, it increases. And then the second rule is that a node can only have up to 2 children because it's a binary tree. The advantage of a binary search tree is that, well, it should be obvious with the name, right? Searching and lookup is very easy to find what you're looking for because if I'm looking for, let's say, number 37, I can start at 101 and say, is 37 less than 101? Yes. Okay, then go to the left. Is 33 less than 37? No. Then go to the right and I find 37. I don't have to iterate in a linear fashion through each node. And that is what lookup means. Lookup simply means that I can search for an item a lot faster than, let's say, an array where I have to iterate and loop through every single item. But what about insert and delete? In a hash table, I can do insert and delete really fast at O1 or constant time. But with a binary search tree, it looks like I can only do O log n. And that should be obvious, right? Because in order for us to insert or delete something in a binary search tree, we need to figure out where to insert the item or where the item is before we delete it. For example, with 105, let's say that we want to delete 105. Well, we have to first, from the root node, get to 105, and then we have to decide which node is going to take its place. In this case, because 54 is less than 144, 144 is going to come up over here. But as you can imagine, this operation, although it seems simple right now, if we had a lot of children and a lot of nested nodes, a lot of reordering needs to happen and shift our nodes around. And don't worry, we're actually going to code this so you understand this, just like we have in previous data structures. But I want to demonstrate, instead of me just using my cursor here, a nifty little tool to visualize how binary search trees work and how their operations are O log of n. We're going to use Visual Go again, and I'll link this, and I highly recommend that you all play around with binary search trees. But let's do a couple of operations here. See that it generated a random binary search tree for me. Let's say I wanted to do an insert, and I want to insert, let's say, the number 1. If I click go, it's going to traverse, figure out where it wants to insert, and it's going to insert 1. What if I want to insert perhaps number 44 this time around? If I hit go, it traverses, figures out where 44 should go, and places it down here. So we're always traversing and figuring out, using O log n, where we should place the item. What about removing? Let's add one more. I'm going to insert 51 this time, so that it places it right over here. Perfect. Now, let's say we want to delete 50 now. If I remove 50, I hit go, I find 50, remove it, and then I have to replace with 51 and go up. So there's a bit of a tough little logic happening there that we're going to have to incorporate. And we're going to get to that. But for now, as I end this video, I recommend that you go to Visual Go and play around with binary search tree so that you get accustomed to it. And as you play with it, see if you notice a problem that we might encounter with binary search tree, because we're going to discuss it in the next video. Welcome back. While playing with Visual Go, did you notice a problem with binary search trees? If not, let me demonstrate something to you. Let's say I keep inserting here. Let's say 86. And then while that's going, I'll also insert 90. And finally, I'll insert 99. All right, what is the problem with this? Well, you can imagine a situation where we have this really unbalanced binary search tree where all the nodes just keep getting added to the right, to the right, to the right, to the right. If we imagine that we didn't even have this section, this all of a sudden turns into a linked list where we're just looping through every single node. This is a big problem that comes with binary search trees. That is, you can have balanced search trees, like the one right here that gives us this log n performance, but then also have unbalanced ones, where it sort of turns into a long linked list, where instead of being able to do the log n operations, you now have to loop through every single node, and lookup and searches become O of n, or linear time. And you even saw in our Visual Go demonstration how slow it took to insert items because it had to loop through so many things. One of the keys that you'll have to remember, and this is a question that you might get asked in interviews, is why an unbalanced binary search tree is bad. And I hope this demonstrates why it's not a good idea. Ideally, we want to balance our search trees so that we can have this performance optimization. If we go to our Big O cheat sheet, we see that with binary search trees, that we have O log of n for most things, which is average. But when it comes to worst case, when we have an unbalanced tree, that all operations are O of n, or linear time. So you might be asking yourself, how do you balance a tree? And luckily for us, there's algorithms that help us do that. It is really advanced, and we will talk about it after we build our own tree and some of the options that we have. For example, we have things like AVL trees and red-black trees that allow us to make sure that our binary search tree is going to be balanced. Luckily for us, they're built in most programming languages, and in interview questions, they won't really ask you to balance a binary search tree because, well, it can get pretty complicated and time-consuming, and interviews usually don't have enough time to get you to do that. The idea is to be able to talk about it and know that there are ways to balance a search tree and be able to talk about the trade-offs just like we did. Now, we're going to talk about these two ways of balancing the search tree in an upcoming video. But for now, let's just focus on the basics. In the next video, I want to talk about the pros and cons of using something like a binary search tree, and then finally implement our own. I'll see you in the next one. Bye-bye. Welcome back. Before we code our own binary search tree, let's just go over the performance implications and why we might want to use it over other data structures. Its strengths are that it has really good performance across the board. You saw that most operations or all operations in a binary search tree are better than O of n, assuming that the binary search tree is balanced. It is also ordered. And because we can place the node anywhere in memory, we can just have flexible size. We can keep growing our tree. The downside is that, as you may have noticed, it has no O1 operation. We usually have to do some sort of traversal through the tree for any sort of operation. So compared to an array, a lookup, for example, will be a lot faster because we have O log n for searches versus if we iterate through an entire array, if the array is unsorted. Inserts and deletes are also faster than an array, unless the array is adding to the end. Otherwise, arrays have to shift all the indexes versus a binary search tree that is just O of log n. What about compared to hash tables? Well, although hash tables allow us to insert and search at constant time, with binary search trees, we have sorted data. And we also have this structure of parent-child relationship that you won't be able to get too much with hash tables. A good thing to keep in mind is that binary search trees aren't the fastest for anything. Remember, their operations are usually always O of log n. On average, an array or an object will have faster operation. But there are certain conditions where they do outperform objects and arrays. So binary search trees do perform really well, as long as you make sure that you stay away from the edge cases that we discussed and we balance our binary search tree. But enough talk, enough slides. I think to fully grasp and understand how trees work, we should code our own. I'll see you in the next one. Bye-bye. Welcome back. It's time to write our own binary search tree. And in this exercise, I'm going to challenge you to write your own before you watch my solution video. Now, keep in mind that just like with linked lists, it's going to require us to keep track of the nodes to the left and to the right of the current node. And also, we have a value associated with a node. I recommend you actually draw this out on a piece of paper to understand, because keeping everything in your head and the calculations might be a little bit difficult. But I have started you here with all the essentials you need. We've created a binary search tree class. We have a node class that we can use. We start our binary search tree with this.root of null because we don't have anything yet. But remember, we have the root, which is our topmost node, which currently is empty. We're going to initialize our binary search tree, and hopefully we're able to create two methods. One is insert and one is lookup. And our goal is to create this tree over here. 9 as the root node, then 4 and 20 as its children, and then 4 has 1 and 6 as its children, and 20 has 15 and 170 as its children. So ideally, if we implement insert correctly, we can say tree.insert 9, then insert 4, then insert 6, then insert, let's say, 20. We'll insert 170. Last two, we'll insert 15, and we see we have 1 left here, so let's do insert 1. And ideally, after running these commands, you're able to create this tree data structure. Now, at the bottom here, I created a small little function for you. And for now, I want you to just ignore it, because we're using something called recursion here, which we haven't gotten to yet. But I only created this function for you to be able to test out your code to make sure that it actually works. All you need to do in order for you to verify that this is working is to say json.stringify, which is a JavaScript specific way to create a JSON string. And we're going to say traverse tree.root. We just give it the root node of our tree, and it's going to traverse and print out everything into a string so that you can check in the console that your tree actually is working. And in the solution video, I'm going to demonstrate how this works, but I've added this as a little helper for you in case you want to double check your work to make sure that it's correct. And by the way, the lookup method should simply return the node that we're looking for. And if it doesn't find the node, then we can return null or false, whichever you want. And I've added the remove method here, which we're going to talk about later because it's a little bit difficult. So for now, just worry about insert and lookup, and I'll see you in the solution video. Bye-bye. Welcome back. Hopefully that wasn't too bad. Keep in mind that when it comes to interviewing, interviewers want you to know that you understand the concepts. You won't necessarily have to code a binary search tree from scratch, most of the time, at least. Because in real life, you have things like this library that somebody else created that allows you to use tree traversal and manipulation techniques. Because this has already been done before. And you can see by using a library like this that you can just use it and create the tree that you want. Most likely, you're not going to implement it from scratch by yourself. But we do want to understand the fundamentals and how it works. So if this was challenging to you, don't get frustrated. This doesn't make you a bad engineer or a bad coder. You're just working towards building those fundamentals so that you can use tools like this in the future and still understand how they work. But enough talk. Let's get to the answer. I want to create a tree that looks something like this. So the first thing I'm going to do is work on the insert function. Now, within this insert function, the very first thing I want to do is to say, well, we want to create the new node. And we'll say new node will be the value. So we're just creating the new node class, instantiating it with the value, and that's our new node now. So we have a reference to it. The first thing we want to check, well, if the tree is empty and there's no root node, well, we should add this as our root node. So I'm going to say this.root equals null. If that's the case, then simply make the root node our current node that we inserted. Nice and easy. And just to check that this is working, if I comment all of this out and click run, there you go. Our root node has a value of 9. Left is null, right is null because it's the only node. And by the way, to show you how this stringify works, it's really, really useful because if I copy this and just point out here that I'm not copying the quotation marks, which makes it a string. And if I open up developer tools in Google Chrome, and I go to my console tab, I can copy and paste this, press enter, and now I have access to this tree. And it's a lot easier for me to view. And once we insert other nodes, you'll see that it's very easy to traverse this tree this way and check your work, which is why I added this function. So we'll come back to that for now. We see that our insert is working, at least for if the root node is null, but let's continue if that's not the case. We'll say else. If the root node is already filled, we'll say that the current node will be the this.root because we're going to have to traverse this node. And we won't know how long we're going to traverse this node for. We just want to keep traversing until we find a place to insert this. And this is a bit tricky, but something you'll get used to when you're building trees. We want to use a while loop, and the condition we're going to use is true. That means just keep looping every time because true is always going to equal to true. And we have to be careful here. If we do this, we want to make sure that there is a way for us to exit out of this loop. Otherwise, we're going to have an infinite loop and we'll crash our little page here. So what are the conditions that we're going to loop through? We want to traverse through the tree. Well, the first check we're going to do is say if value is, remember value is what we insert, if that is less than the current node.value, so we'll start from the root node and say, hey, is the value that we're entering less than the current node value? If that's the case, we know the rules, so we're going to go left if the value is less than the current node. Now, in here, we want to check, first of all, if there's no current node dot left. Is there an element already to the left of the root node? Because if there isn't, in that case, we can just assign the current node dot left to our new node that we want to enter because there's nothing there. And we can just return out of this loop and just return our this, which is the binary search tree. However, if there is something to the left of our node, let's say in this case 9, in that case, we'll say current node is going to equal current node dot left. So we're going to update and shift over so that the current node is no longer 9. It's whatever is to the left of 9. And that's going to keep us looping. So we're just going to keep looping, keep looping, keep looping until we hit a node that doesn't have a left-hand side so that we can place the current node or our new node into its place. But that's for the left side, if the value is less than the current node. If the value is greater, or in this case equal to our current node, And we can decide here where we want to place values that are equal. That's up to us and how we want to implement it. We'll say that we'll go right if value is greater or equal to current node. In that case, well, we want to do the first check first, which is if current node dot right, there's nothing to it, there's nothing next to it, to the right of it. In that case, just like above, we can say current node dot right equals the new node. And we're also going to return this because we want to stop looping. Remember, as soon as we have a pointer to null, that's when we want to exit out of this while loop that's going to loop forever. Otherwise, we simply say current node is going to equal current node dot right. And there you go. Hopefully this works. But before we test this out and see if we made any minor mistakes, I do want to warn you. If you are just coding along, I encourage you to pause the video and think through line by line, maybe even drawing things out, maybe using Visual Go to see what we're doing. Because it's really hard to keep this in your head. Even myself, I can't code this from scratch. It takes me a bit of time to think things through and see how we want to structure the code. So don't feel frustrated if this is a bit overwhelming. I encourage you to pause the video, try to code along and understand what's happening step by step. All right, let's test this out. I have an insert of 9 here. If I click this run, that's working. If I insert 4, all right, looks like 4 got inserted. What about 6? All right, I'm just going to comment all of this out and see if that works. I'm going to click run. All right, looks like we've logged out everything, but I want to test, make sure that everything is working as expected. So what I'm going to do is I'm going to copy and paste this, remember, without the quotes at the end, because I don't want to copy the string. I want to copy the object, and I'm going to, again, open my developer tools, go to console, clear my code, and then just copy and paste, hit enter, and now we can test our tree. Let me scroll down here. This is the tree that we want. We have 9 at the top. To the left and to the right, we have 4 and 20. Look at that, that's good. And when we go to the 4, we have left is 1, right is 6, awesome. And 1 should have null null to the right and left, perfect. Same with 6, perfect. And if we scroll down, let's look at 20. It should have 9, or it should have 15 and 170 as its children. We have 15 and 170, and both of those pointing to null. Hey, not bad. Not bad at all. It wasn't too bad. Once you get a hang of it and code this on your own, you'll see that it makes sense. It's all just logic and something that we've learned when working with linked lists. In the next video, we're going to try and tackle lookup. If you weren't able to implement insert, please try and do that now before we get to lookup. Otherwise, try to implement lookup on your own, and I'll see you in the solution video. Bye-bye. Welcome back. Let's try and implement the lookup function, or the search function. We want to check if an item or a node exists in our tree. Let's see how we would go about this. The first thing I would want to do is to check if there is such a thing as a root node, if it's empty. So I could have done this .root equals null to check if the root is empty, or I can use the exclamation mark in JavaScript. And we'll just say return false, because if the root doesn't exist, then it doesn't really matter. We're not going to find that node. Otherwise, we're going to say, once again, let current node equal to this .root, very similar to what we did above. Remember over here. And you'll notice some similarities with what we did when we did the insert. We still need to traverse through our tree. But instead, our while loop is going to stop whenever the current node no longer exists, or we no longer have a node to go through. Because once we've gone through our binary search tree and it's null, that means we didn't find what we're looking for. So in this case, I'm simply going to say if the value that we're looking for is less than the current node dot value. In that case, current node is going to equal current node dot left, because we now want to go left. If the value is less than the current node value, that means it's not the same. It's not the node we're looking for. So go left, because that's where I can find something that might be less than the current node. otherwise. And we'll use an else if statement here, which says another condition. So if that doesn't match, if the value is greater than the current node dot value, what do you think we do here? Well, we go to the right. So we're going to say current node is now going to be current node dot right. So we can keep checking to the right of us. And then finally, else if, that is another condition, and we can say if current node is dot value equals the actual value that we're looking for, that means we got a match. That means that node exists, so we're just going to return the current node. Nice and simple. And then finally, because we're not returning anything, we're just looping through the while loop until we find the current node, where we return the current node, or current node becomes null because we cannot find anything. If we don't find anything, just return false. The only way we return something other than false is when we find our node with the matching value. So let's see this. If I now run tree.lookup 9, and I'm going to comment this out because we don't need to check that our tree is being made. If I click run, there you go. I get the 9 node that has reference to all the other nodes beneath it. If I look up 90, I'll get false because it doesn't exist. What about 20, which exists? Yep, we found 20. What about 170? Yeah, we found 170. It's a node, but has no left and right references because it's a leaf node. And then finally, 171 is false because it doesn't exist. Well done getting this far. Hope you're able to implement your own binary search tree. Once you get the hang of it, it's really not that bad. At the end of the day, each line should make sense, and traversing a tree should make sense to you by now. We also understand why we have big O of log n. Although we have loops here, like while loops, we're not actually iterating through every single node. We're only iterating using divide and conquer, something that you'll hear a lot of. Divide and conquer simply means we're dividing up so that we don't visit all the nodes. Each node that we visit, we make a decision to go left or right. I'll see you in the next one. Bye-bye. Welcome back. We have a bit of a bonus exercise. Now, you can skip over this exercise because it is a little advanced and you most likely won't encounter it in an interview. But for those who are curious, that is how to implement the remove method in here. If we wanted to remove an item from a tree, how would we go about doing it? Now, if you want to try and implement this, I want to give you a heads up. The best way for you to visualize and see what steps we need to do is to go back to Visual Go. Make sure that you move the speed to the slowest so you see what's happening. And you start removing some nodes to see what the logic is in removing nodes. Some steps are really easy. If we wanted to remove one, for example, we simply traverse and find one and just remove it. But then there's other cases that gets really complicated, such as what do we do when we remove 51? Well, if I click play here and say remove 51, well, you'll see that we're going to start traversing to find 51. And notice what happens when we find 51. We actually keep going to 55, and then we keep going to 54. And watch this, we split things and move 54 up. And I know that's really, really confusing. You might want to do this a couple of times to see what the logic is. But essentially what we're doing is we're finding what we want to replace, going to the right of it, then the left, and placing that left item to the top. Like I said, this is going to be a little bit advanced. But if you want to challenge yourself using the Visual Go animation, try to figure out how to implement your own remove method. And in the next video, I'll show you my solution and go over the steps that we take for this to work. I'll see you in the next one. Bye-bye. Welcome back. How was the remove method? It was pretty tough, wasn't it? Now, I don't expect you to be able to get this. Even for me, it took quite a lot of time to get this working. And I'm going to give you another chance to finish it if you want. I have my code minimized here just to show you the if statements and the steps that I'm taking. So you could always pause this video. But let me just go over the steps I'm going to take. And usually I like coding step by step. But when it comes to this function, it's really, really hard to go step by step when you're not coding yourself or you don't have a diagram to point to and show. So I'm going to leave the code for you so you can implement it on your own and actually, like I always recommend, draw it out with a piece of paper to understand what's going on. Otherwise, if I just coded this along, it would be a 30-minute video of you getting bored, and then you're not going to have fun with data structures anymore, and we don't want that. So all we're doing is, well, if we remove, we're going to check if there's anything in the root. If there isn't, well, the tree's empty, there's nothing to remove, we're going to return false. Otherwise, we're going to grab the current node as this.root first, and then we do something new here that we haven't seen before. We declare a new variable called parent node. And this is something you may have realized as you coded this along. We need a reference to the parent. Because if we remove something from here, such as 14, well, we need to, before we get to 1, get a reference of 14 so that when we get to 1, we have access to 30 so that we can link 30 to 1. So if we go back here, now that I have parent node variable, and I do my loop to check if the value is less than the current node, in which case I'll go left, and this should be familiar. But this time I'm also keeping track of the parent node. And otherwise, if we need to go to the right, well, then we go to the right, but also keep track of the parent node. Now, this is the interesting part. We're looping through everything here and nothing's too crazy until we get to a match. Once we get to a match and we find the current node that we want to delete, we have a match, we need to get to work. And we have 3 options here. The first option is that the current node has no right child. If the current node has no right child, let's have 55 as an example, or let's do 14 as an example. If I remove 14, you saw that all we did was we remove 14, but we kept a reference to the parent node and just moved 1 up. That was nice and easy. And in here with option 1, that's really all we do. We first make sure that the parent node doesn't equal to null. That means we're modifying the root node. Otherwise, the root variable gets updated to our current node. Otherwise, if parent is greater than the current value, then make current left child a child of the parent. If parent is less than the current value, make left child a right child of the parent. Again, I know this is confusing, and like I said, this is something that you might have to go on your own. I'll leave comments out here for you so you can actually play around with it and play around with Visual Go so you understand what's happening. So that's the first option. If that's the case, then do that. If the right child, if we have a right child, but that right child doesn't have a left child, let's find an example that has that. So we have a right child that doesn't have a left child. So that is 54. What happens when we remove 54? If I click on this, 54 gets removed, and we just place 55 instead of 54 now. So in that case, we go, again, check if the parent node is not null, so that we have to replace the root node. Otherwise, we go through similar steps to reassign the node. What about the last option? Right child that has a left child. So if we go here, we have a right child. Let's say if we want to delete 30, that has a left child, 38. So if we want to delete 30 and hit go, we still traverse until we get to the left. And then, oh boy, we do a bit of a magic. This will require you to read through the code, and I've left some nice comments for you so that it makes sense. But we're essentially finding the right child's leftmost child and looping through this, changing the subtrees of the tree. Like I said, this is quite a bit advanced and really hard to explain just on the screen. So I do recommend, if you weren't able to get the remove function, to go through this step by step. I'll link to the code right in the resources so you can play around with this and see that it works. But to check that remove does in fact work, let's say I'll remove 0 from this list. If I click run, I get undefined because there's nothing to remove. But if I remove, let's say 170 and I click run, I get true. And if I traverse our list and try and grab our tree now, Let's open up Developer Tools. Paste this, press enter. And now if we go to 9, 20, and we see that the right node is now empty where 170 should have been. So we're able to delete the node successfully. That's enough for now. You can play around with the remove method if you want. You can try and code it yourself. It will take a bit of time. I know I keep saying this. I do encourage you not to get disappointed if the remove method was really difficult. I didn't really want to include it in the course because it is overly complex and not something you want to get too worried about when it comes to an interview. But I thought some of you might be interested in it. Just make sure that it's not something that discourages you. As long as you can do the inserts and lookups, that's what matters for interviews. I'll see you in the next one. Bye-bye. Welcome back. Now that we've implemented our binary search tree, I want to talk a little bit about balancing our tree. Usually in production, you want to have a balanced search tree. There are two types of trees that are very popular when it comes to this. Although we built our own binary search tree, you'd most likely in production use something like an AVL tree or a red-black tree that automatically rebalances itself so that we don't have those edge cases where our balanced tree turns into a linear unbalanced tree. Now, these topics, we don't need to code ourselves because they are a little bit complex, and most of the time you're using some sort of a library that implements it. But I do want you to understand how it works, so I'll leave resources for you for both red-black tree as well as AVL trees, where if you click here, you see that Visual Go also has it. To demonstrate for you how it works, if I want to insert, let's say, 77 into my AVL tree, nothing's different. We're adding 77 to the tree. But if I now add, let's say, 80, which will make our tree a little bit unbalanced. If I hit Go, you'll see that I'm traversing down, I add 80, and then all of a sudden, oh, it's unbalanced. It's going to go back and do a little bit of a switch or rotation to balance out the tree, to make sure that the levels that we have in a tree are always balanced. And then we have red-black trees as well, which does things a little bit differently. If, let's say, we inserted 9 here, then let's say we insert 10. And then finally, let's insert 11. You'll notice that, oh, it's not balanced. We need to balance it out. And once again, automatically make sure that our tree does get balanced with something called red-black tree. As you can see, the nodes are red and black here, and that's something that we use to keep track of when we need to rebalance. I'll leave resources for you if you want to learn more about them. Just keep in mind that these two are usually the most popular for balancing binary search trees, and in interviews, you won't have to implement them. You just need to be able to talk about them and why they are useful, something that we should know by now. I'll see you in the next one. Bye-bye. Welcome back. We've talked about binary trees, binary search trees, and then we learned about how to balance those trees and some of the time complexities involved with a BST. And I want to talk to you about two other common type of trees. One is a heap, and the other one is a trie or tree. In this video, let's get talking about heap. Now, when it comes to heap, we're most likely going to talk about binary heaps. Just like we had with binary trees, that means there's only going to be 2 children to a node. Now, why are these useful and how are they different from binary trees? Let's go have a look. A binary tree, every child belongs to a parent node that has a greater priority or value. If you look over here, every child, that is 72 and 33, is lower than 101. 72 is higher than 2 and 45, and 33 is higher than 5 and 1. This is actually called a max heap. There's also something called a min heap, which is the exact opposite, where the root node is the smallest. Now, this value can be anything you want. It can be a person's name, it can be a number, it can really be anything because it's a node. But as you can see, all we're dealing with is that in a binary heap, every node on the top level has a greater value than every node on the next level down. And a heap can be used in any algorithm where ordering is important. And as we're going to discuss, it's commonly used when it comes to priority queues. Now, with arrays, we had random access. It allowed us to randomly access any element within them using an index. In a linked list, we can change things dynamically, unlike an array, but finding something within them is O of n, linear time, because we had to go through the linked list. Heaps are a little bit different. You can't do O of 1 random access like we did with arrays or hash tables. As we know about trees, we have to do some sort of traversals. Now, compared to a binary search tree, we see that, well, lookup is O of n. It's not O of log n, because it's less ordered than a binary search tree, right? A binary search tree actually had meaning between left and right child. The left was always less than the right. In a binary heap, that doesn't matter. Left and right can be any value as long as it's less than the top value. So if we're looking for, let's say, 1, we have to check the parent node. Then we have to check, because 101 or because 1 is less than 101, we have to check both nodes underneath it. And then because 1 is less than 72 and 33, we have to once again check every single node. And looking for 1 becomes O of log n. So it pretty much turned into searching through a linked list or iterating through an array. So why would we ever want to use a binary heap? Well, it turns out that binary heaps are really, really great at doing comparative operations. Just like saying, I want people that have a value over 33. Because in that case, we can just grab these items quite easily instead of going all the way down through the nodes. Heaps are actually used a lot in data storage, priority queues, sorting algorithms. So let's have a look at how a binary heap is implemented visually. We have a binary heap here using Visual Go. And if we wanted to add, let's say, insert 26, we hit go. All right, that was really fast. But what if we wanted to insert, let's say, 51? If I insert 51, I had to do a bit of a switch. You see, heaps add value on the tree in order from left to right, and then bubbles up if it's not in the same order or the priority order that it wants, kind of like we did here. So if I add, let's say, 70, or you know what, let's add 100. What do you think will happen? Well, if I hit go, you'll see I add 100 and then it bubbles up. So as you can see, inserts, although it looks fast, can still take log n. And this is the same case with deletes as well. It's O of log n. Now, in order to truly understand why we need something like a binary heap, why they're so useful, how they're different from binary search tree, we need to talk about priority queues. So let's talk about priority queues. Welcome back. I wanted to add a quick gotcha when it comes to heaps. That is, when you hear memory heaps, that's not the same as the heap data structure. You might have heard of memory heaps in something like a JavaScript runtime engine, where we have a stack and a heap, the two locations where we are able to keep memory. Now, this heap, you can think of as free storage, is a region in our memory where we can store arbitrary data. Languages like C also have this heap. Now, the naming is just coincidental, and heap has no real relationship with the data structure that is named heap. Keep that in mind. Heap is simply a heap of memory if you're talking about a language runtime, for example, versus a heap data structure, which is what we're talking about now. I wanted to clarify that for you because when I was learning about heaps, for some reason, I always thought they were the same thing, but they're not. Just throwing it out there. I'll see you in the next video. Bye-bye. Now, we learned about binary heaps. And we mentioned that unlike a binary search tree, there's no order from left to right. This 33 and 77, we can swap them and it'll still be a binary heap. The beauty of binary heaps is that they take up the least amount of space possible because it's always left to right insertion, as we just saw. So there's no concept of an unbalanced binary heap. We don't have to rebalance it like a binary search tree. Because of this, because they do left to right insertion, as we saw in the previous video, they preserve this order of insertion, which is pretty amazing, right? And you can actually implement binary heaps using arrays versus what we did before with binary search trees where we used nodes. So the only guarantee that binary heap gives us is what I mentioned. The parent is always greater than the children. Now, besides being memory efficient and just compact because it's always a complete binary tree, binary heaps are really, really useful for things such as priority queues. And you might be asking yourself, priority queue, didn't we just learn about queues and isn't that the same data structure? Well, no, because with queues, we just assumed that it was first in, first out. You were the first person in line, you should get to go first into the roller coaster or the movies. Priority queue is something different. It is a type of data where each element has a priority. And elements with a higher priority are served before elements with lower priorities. You can think of this as a club. Let's say we have a nightclub that is very, very popular and there's a long lineup. And we let some people in. Everybody's happy. But then all of a sudden, we have some VIPs that showed up. Well, they pay a lot more money than the other customers, so we're going to let them in first. So now we have a different priority, where even though they arrived later, they get to go in. They have higher priority. Another good example is an emergency room. You want to treat the patients that have the most severe symptoms or conditions, right? Another way to think about it is, let's say we're lining up to get into an airplane. We have the first person coming in, lining up, and then all of a sudden the captain shows up. And because the captain should get on the airplane before a normal passenger, the captain gets now put as priority, as the root node, because the value is higher, or at least in this case, the value is higher than the passenger. So let's say another passenger comes on. Because we're doing left to right insertion, we put the passenger to the right. So now we know we're going to let the captain go in, then the first passenger, then the second passenger. Next, we have a stewardess that came in. He or she should get to go before the passengers, but not before the captain. Well, in that case, once again, we place the stewardess below the captain, but to the right or to the left of the passenger. And then we have another passenger that comes. We do left to right insertion. We see a right spot down here, so we place them down here. So we see how everything gets balanced, which is nice, but it's also really, really easy for us to now let people into the airplane because we know the order. We go from the top, then left, then right, then left, then right, left, right, and we just keep going, keep going, keep going. We know the priority very easily. I'm sure you see where this might be useful in a lot of situations. To review, we learned what binary search trees are. They're great, but sometimes binary heaps or priority queues are even better. Although searching through a binary heap is a lot slower than a binary search tree, you have an idea of priority because insertion is done in order. So you know who should be first, who should be second, who should be third. And although we might have to bubble up inserts every once in a while if there's somebody that has really high priority, most of the time you get really fast inserts with binary heaps. And as we mentioned, lookups are slow. But you want to use binary heaps when you're just interested in finding the max or finding the minimum if it's a min heap. And a lot of the times in binary heaps and priority queues, you have a method called find max or find min that is O of 1 because you know right away that the top root node is the max or the minimum. So for those operations, it's really, really fast and great. And there you have it. I'll see you in the next video. Bye-bye. Welcome back. We have one last tree that I want to talk about. And that is a Trie, or a tree. Pronunciation here varies on who you ask, but let's have a look at what it is. A Trie is a specialized tree used in searching, most often with text, as you can see here. And in most cases, it can outperform binary search trees, hash tables, and most other data structures we've been talking about, depending on the type of search you're doing. And just by looking at this image, you might understand what it does. Tries allow you to know if a word or part of a word exists in a body of text. You see, a trie has usually an empty root node, which is the starting point. And from there, letters are added. You see that it's not a binary tree. It can have multiple children. In this case, it'll most likely have 26 children because there's 26 letters in the alphabet. The power of the trie is when we search for something such as N. If we had this dictionary, we know right away that there's 2 words associated with the word N. Another name for a trie is something called prefix tree. It's a tree-like data structure which proves to be quite efficient in solving these problems specific to strings. You can think of it as autocompletion, right? When you search something on Google, it knows what you might be searching for, or it tries and completes the word for you. And this is what it's used for searching words in a dictionary, providing auto-suggestions on search engines, or even IP routing. If I typed in A, I know immediately that all the children are related to A, and I can print out ARE and then AS. The benefit of this type of data structure is speed and space. What do you think the big O of finding a word in this data structure is? We're not going to go through every single node. Instead, all we need to do is find the length of the word. So the big O of a trie is O of length. That is the length of the word. If I'm looking for the word R, A-R-E, all I do is look for A, then look for R, then look for E. All I'm doing is hitting 3 nodes which are associated with the length of the word. When it comes to space complexity, tries also have a major advantage. Because we use prefixes, such as N here is used in different words, and same with A, we don't have to store it multiple times. It's stored in one location and you have children linking to it. Because of these prefixes, you save a lot of space. Because you don't have to store the word not in use, you get to avoid storing that extra N. Although there are a ton of trees, as you saw, and we even talked about a lot of trees, the way they work though, beyond some small logic, such as the differences you saw in binary search trees and binary heaps and priority queues, as long as you understand how to build one from scratch like we did, the small variations are fairly easy to pick up, so that now you have the ability to construct other trees as needed. Remember that Wikipedia page with a ton of tree data structures. They shouldn't look as intimidating to you anymore. At the end of the day, they're just tree structures with a few different rules applied to them. Something that you should easily be able to do with a bit of research now.